So this video is going to be on how to calculate capacitance from electrochemical impedance spectroscopy data. So just to start off with, what is EIS? So in short, EIS involves applying a small alternating potential wave over a range of frequencies and observing the resulting alternating current. So this is the basis of what's going on. In red, we have an applied potential, that is a sinusoidal wave. And from that, we have a sinusoidal resulting current response that we measure and look at. So these are some examples of what the data is typically presented as. Most of the time it is in the form of a Nyquist plot, but also in the form of a Bode plot. The Nyquist plot involves putting the real impedance on the x-axis and the imaginary impedance on the y-axis. How do we get to these Z impedance values? I'll go into more explanation into the video, but basically because we have two sinusoidal waves and they are out of phase with each other, we need to have an imaginary component that accounts for the out of phase part. Again, I'll get into that a bit further on in the video. So let's move into the capacitance part of electrochemical impedance spectroscopy. So just starting off, we are quite familiar with cyclic voltammetry. We have an applied potential and we measure the current, which looks something like this. To find out the capacitance of our voltammogram, we know that the area underneath the curve equates to the amount of charge passed, which is over here. And with that, we can find out the capacitance by dividing it by the applied potential. So keeping this in mind, we have for impedance the two sinusoidal waves, and we measure the current. So just like capacitance, we put the current on the y-axis and the potential on the x-axis, and then we get something that looks like an ellipse. The ellipse looks like this and corresponding to the applied potential and the resulting current. And it looks somewhat similarly to a cyclic voltammogram, but as an ellipse. So if that is our voltammogram, all we need to technically do is integrate the area under the curve to get the amount of charge passed, and then we can find the capacitance by dividing it by the applied potential. So that is what we do in short, but obviously it's easier said than done. So we need to take more of a mathematical approach. Okay, now let's move into the background of impedance. So as we know, we apply a sinusoidal potential wave that can be represented by this equation here. And we know that the resulting current is offset by a certain amount. This offset is represented by phi, otherwise referred to as the phase shift up here. So if we know this is our potential wave, we can then represent the current wave, with this equation here, and we include phi because we know that it is going to be offset from the input potential wave. So with a normal direct current applied potential, we have a one-to-one version of the current from the applied potential. So it is in phase with each other. But as we've talked about here with impedance, it is out of phase with each other. So we need a new way of talking about the resistance like we do in Ohm's law here. We can no longer use R for resistance because we have an out of phase component, and that out of phase component is used to refer to the imaginary part and the real, and we also have the real part, which is the actual response that we get. So that's how we end up with our imaginary and real components, and we'll get into the math side of that in just a second. Please feel free to skip this part if you want to just get to how you get the capacitance from your data, but just going into the background of it, of how we arrive to the final equation of getting your capacitance from your data. So as we've already discussed, these two equations here are used to represent our applied wave and our measured wave. So if we recall Euler's formula, where we can take an exponential that is written in this form, and we can put it into the form of cos x plus an imaginary number times sine x. We can therefore convert these with Euler's method into the exponential form. So that will come out something like this. And from that, we can then apply it to Ohm's law over here. So we obviously need to convert it, as we spoke about before. We can no longer use the resistance term to describe our system since we have our phase shift. We need Z to account for the imaginary out of phase part. So if we have this and then plug in our converted Euler's form of the equations into here, we arrive at something like this. From that, we can cancel out the common denominator, which we have e to the power of the imaginary number times omega t, same on top here, but don't forget we still have phi out the front, out here, so this will still remain, so we get something that looks like this. So as we know the exponent rule, just a quick reminder here, we end up, because it's on the bottom, we can denote it with a negative to the power of a negative to imply that it is still on the bottom. From there, we can make this, we know that this is equal to the modulus of Z. So from that, we can then sub in this into here. So then we end up with this. And then from that, we can convert it again with Euler's formula and going from this form into now this form. So then we get something that looks a little like this. Now, don't quote me here, it has something to do with it revolving around the axis or something, but this negative here becomes a positive. I am not super strong on my maths, but there is a reason for this being changed. But we basically arrive at this equation here. From that equation, we can then split them up to the real component, which is this one here, versus the imaginary component, which is this one here. And that's how we basically go from our equations of the two waves into splitting them into the real component and the imaginary component. And that's what we get with our what we plot with our Nyquist plots. So now that we've finished the heavy maths part of it, we can move back to finding out how we get the capacitance from our impedance data. So here we just have a simple Cartesian plot with our y and x axis. A single point here is represented by this here. So if we transfer that into polar coordinates, our y becomes r sine theta and our x becomes our cos theta with a radius here and degrees here. Why is this important? Well, from our real and imaginary components that we came to terms with previously, this can be transferred into polar coordinates because we have a sine theta, a cos theta, and a constant out the front. Basically, all we care about is that the real component comes down on the x-axis and our imaginary component becomes the y-axis, with the modulus of z becoming the radius in the situation and our theta becoming the phase shift. Don't stress on this too much. All we care about is that it forms a really nice triangle. Okay, so we've agreed that we can form a very simple triangle from a single impedance data point here. If we have a triangle, we can apply basic trigonometry to it. So if we want to find an angle, which is our phase angle in this scenario here, we have an adjacent side and an opposite side, which means we can use the inverse of tan here to find the phase angle. Similarly, we want to find the hypotenuse here, and we have an A side and a B side, which means we can use this equation here to be able to find the modulus of Z here. Okay, so remember from before, if we integrate the area under the curve, it equals to the amount of charge passed. And if we put the amount of charge passed over the applied potential window, we can find the capacitance. So from our two equations that we used before for the two waves, for the input and output, and if we use Ohm's law, but then rearrange it to have our resistance or our modulus of Z by itself, and if we solve to get I by itself, we have something that looks like this. We can then sub this value of I into this equation for the current response, and then it will look something like this. So all I've done is just shove this into this, and then we end up with this. So we then can use this to find the area under the resulting current curve, which looks something like this. All we've done is just taken this out the front because it's a constant and left this inside the integral. So that then simplifies down quite nicely to something quite simple. And if we know that this is the amount of charge passed, then we can sub it into this equation here to find the capacitance. That will then look something like this, which we're then able to cancel out the potential, and then we are left with something very simple for the capacitance. This is what you want to use for calculating your capacitance from the impedance data, and please refer to this paper here, which talks about how this is done and the limits that are used for the integration. But if you have some impedance data, all you want to care about is using these equations here to get your unknowns and then to plug them into this equation here, and then that will calculate the capacitance from your impedance data. So if you apply what we just talked about, you'll get some data that looks like this with your capacitance on the y-axis and log of frequency on the x. For this experiment, we did quite a few frequencies. I think it's very important to do that instead of focusing on a narrow frequency range. Otherwise, you're going to miss important information. For another experiment, we measured the impedance for every 10 millivolts over the potential window, and we've plotted the capacitance versus the potential, and you get some quite interesting data here. But each line basically is a decrease in the frequency. Please consider subscribing, as I plan to do a tutorial on applying this to some actual data, so hopefully it will be easy to follow along and apply it to your own work. Thanks for watching. Cheers.